So let's consider now another example of the 1D heat equation, except in this example, let's put the left end of the bar in ice water and the right end of the bar to be insulated. If you remember, when an end of the bar is in ice water, that means that the temperature is held at a fixed value for all time. So for example, in ice water, the left end would be held at 0 temperature for all time. If an end is insulated, then it's not the temperature that's held fixed, but rather it's the derivative of the temperature with respect to x that is held fixed. And in particular, that's held at 0. So no heat is flowing into the bar at the right end. That's what that condition tells us. So let's try and solve this 1D heat equation with these different sets of boundary conditions, and then an initial conditions given here, something that looks like 3 sine of 5 pi over 2L times x. Since we've modified our boundary conditions, we need to go back and redo the separation of variables strategy that we had used for the heat equation before. But actually most of it we're pretty comfortable with. In fact, the first few steps, taking an ansatz of x times t and plugging that into the partial differential equation, well, that part doesn't really depend on the boundary conditions. But the value of the separation constant does depend on the boundary conditions. So we're going to pick up there. So in particular, by making our ansatz and plugging that ansatz into the differential equation, we get these two differential equations, x double prime over x is equal to lambda, and t dot over t is equal to alpha times lambda. And we're supposed to use our boundary conditions to determine the sign of the separation constant. As before, we can have 3 different types of values for lambda. Lambda could be 0, lambda could be negative, or lambda could be positive. You're going to examine lambda equal to 0 and positive in a separate context on, say, a homework. So let's focus right now on lambda less than 0, which means that our x function is a cosine of kx plus b sine of kx. We want to impose our boundary conditions on this solution. So let's impose the boundary condition at the left end first. So at the left end, the temperature is set to 0 at x equal to 0, and that tells us that a is equal to 0. So we're just going to get rid of this whole first term, leaving us with x of x is equal to b sine of kx. So far, everything is the same as we had done before. Now let's see what happens when we impose our other boundary condition. So if we impose our other boundary condition at x is equal to L, we first have to take the derivative of u with respect to x, and then plug in x equal to L. So let's do those separately. The derivative of u with respect to x is kb cosine of kx. And then we impose x equal to L there. That tells us that kb times cosine of kl must be equal to 0. Well, one solution of this could be that b is equal to 0, but of course we don't want that solution. That tells us that we have no solution for x of x. So instead we're going to choose the possibility that k times L is equal to n pi over 2, where n is some kind of odd integer. That would ensure that cosine is always 0, and so that would ensure that we can always solve this boundary condition. Okay, as before, we have figured out a value of k, the separation constant, that will allow us to solve our boundary condition, but we haven't figured out what b is, that arbitrary constant b, and that's similar to what we had done before. We didn't have a solution for that. So we figured out a solution for capital X of x, including the value of the separation constant. All we need to do now is find a solution for t of t. So what we need to do is we need to take our t differential equation, t dot over t is equal to minus alpha times k squared, and solve that ordinary differential equation for capital T. This differential equation is one that we know how to solve. In fact, we can solve it using the general techniques of first order differential equations. So one way we could do that is multiply by little dt on both sides and then integrate both sides. Solving that for capital T of t gives us capital T of t is equal to c e to the minus alpha k squared times t. If you don't see that step, there's a couple steps in between there. There's a natural log on the left-hand side, and then you have to take the exponential of both sides in order to get to this. It's worth working through those extra steps to make sure that you feel confident with that. We can actually go one step further for this solution for t of t, because we know that what the value of k is from our previous solution for capital X. And so plugging in k is equal to n pi over 2L for n odd, plugging that into the value of k in the exponential gives us a general solution for capital T of t that looks like this. There's a lot going on in the exponential there, but most of them are just constants. We have an n squared and we have a t. Okay, so now we've solved for capital X and capital T. So let's put this together and find the general solution. Take a moment to pause the video and see if you can write down the general solution from these solutions here. Okay, hopefully you paused the video and worked that out. Let's do that ourselves now. Let's first multiply our solutions for x and t to get the solution for u of x and t when we multiply those two. And when we multiply them, we can combine the constants b and c into a new arbitrary constant, which I'll just call b twiddle here. And then I have my sine function and my exponential. The general solution is a sum of all sets of possible solutions like this for all n values that I'm allowed to choose. But remember, I'm only allowed to choose odd n values, so I have to restrict my sum to the odd n sums. But my general solution then looks like this. I'm just going to change that b twiddle into a b sub n, because in principle, each of these terms for different n's can have a different coefficient out in front. So we have now solved for the general solution to the 1D heat equation using separation of variables with these new sets of boundary conditions. It doesn't look all that different from what we had with both ends immersed in ice water, except now we have odd ends that we're using instead of all ends. So let's go back to our original question, which is to solve the 1D heat equation for these boundary conditions with the initial conditions that the temperature at T is equal to 0 is 3 sine of 5 pi over 2L times x. So we need to find the unknown coefficients, the b sub n's. So let's take our general solution and put t is equal to 0. Well, we put t equal to 0, we get e to the 0. That's just 1. We still have our b sub n's and our sines. And so in order for us to solve for this initial condition, we see that we must have b sub 5 is equal to 3, namely for n equal to 5. And b sub n is equal to 0 for any n that's not equal to 5. So our solution for all time is just picking up one term from that infinite sum of terms, the n is equal to 5 term. So we have 3 sine of 5 pi over 2L times x. And then in the exponential, we put n is equal to 5, so that n squared gives us the factor of 25 that's there. We still have alpha, pi squared, t, and then divide by 4L squared. So this gives us a solution for all time.